Thank you very much. So thanks, first of all, the organizers for giving me the opportunity of presenting my work today. So this is going to be some other aspects on the exact factorization that has been presented on Tuesday by Hardy Gross. And so I'm going to mainly focus on how we use the exact factorization to derive molecular dynamic schemes to simulate ultra-fast non-radiative phenomena in molecules. So basically, the context of the field of application of what we want to do is basically photochemistry. So in photochemistry deals with chemical reactions that are activated or driven by light. And so this is just to give you some schematic representation of the phenomena that we are interested and we would like to be able to describe in simulation. So here I represent what we call like these surfaces here, what we call the adiabatic or Born-Oppenheimer surfaces or potential energy curves. And they represent the electronic energy levels as functions of the nuclear nuclear coordinates. And in this case, I'm just working in one dimension. So the nuclear coordinates, I suppose here being the internuclear distance of a diatomic molecule. So you see here I show some blue and red potential energy curves, which are labeled with the S and T. So these are electronic states associated to a spin singlet character or a spin triplet character. And so basically what happens when a molecule is excited by light, for instance, ultraviolet or visible light. So starting from the ground state, the molecule absorbs photons and it's excited to an excited singlet state. And then the molecule can relax via non-radiative pathways. And so these non-radiative pathways are represented here by the wiggly lines. And so we have here in green what we call internal conversions, which are non-radiative pathways involving spins or involving states with the same spin multiplicity. And these kind of pathways here, they are mediated by the non-adiabatic couplings between electronic and nuclear motion. So these kind of events happen beyond the Born-Oppenheimer approximation or beyond the Born-Oppenheimer regime. In pink here, instead, they're represented what are called the intersystem crossings, and they are instead, they take place between electronic states of different spin multiplicity, and they involve, in fact, they are mediated by spin orbit coupling. And so it's these kind of events here, internal conversions and intersystem crossings, that we would like to be able to describe with a molecular dynamics like scheme for in molecules or isolated molecules. And so basically now I'm going to focus on basically internal conversions. So just to set the stage a bit of the formalism, I will recall in one slide the exact factorization. Okay, so that Hardy Gross has presented already in various aspects on Tuesday. I'm going to focus a bit more today on this part here on the approximations. Okay, what are the approximations that we have to introduce to the exact factorization to come up with a scheme that we can actually implement and use to simulate molecules. And this is going to be the main part of my talk. And just at the end, I'm going to mention some of the problems that we can deal with and that we have described so far. So what we want to do is to solve the time-dependent Schrödinger equation here for a system of interacting electrons and nuclei. Here the Hamiltonian, the molecular Hamiltonian contains the nuclear kinetic energy, and the electronic Hamiltonian contains the electronic kinetic energy and the interaction potentials. And the psi here is the molecular wave function. And without doing any approximation, we can write the molecular wave function as a single product here of a nuclear wave function and an electronic term. So now the nuclear part depends on the nuclear positions and on time. And it's a proper nuclear wave function because as I will show you in a second, it evolves according to a time-dependent Schrödinger equation. And instead here, the electronic wave function, the electronic term is not really, well, a wave function. It has this weird parametric dependence on the nuclear configurations, but it depends on electronic positions and on time. And so when you plug this product here into the time-dependent Schrödinger equation, you obtain these two evolution equations. So as I said before, the nuclear equation contains here, is a real time-dependent Schrödinger equation because here in square brackets you have a Hamiltonian. And in this Hamiltonian you have, so this is the nuclear momentum, and this is a vector potential that depends on time. And this is a scalar potential that also depends on time. And both of them, they depend on the solution of the electronic equation. The electronic equation is, again, an evolution equation, but it's not a time-dependent Schrödinger equation, especially due to the presence of this operator here, an electron-nuclear coupling operator that depends explicitly on the nuclear wave function. So to solve the electronic equation, we have to know the solution of the nuclear equation. And I'm going to say and to look a bit more into the details of this operator here in the next few slides. So now, how do we develop a quantum classical, let's say, hybrid or quantum classical dynamical scheme to solve the two equations here? So the first step is basically to switch off somehow the quantum nature of the nuclei and to replace the time-dependent nuclear Schrödinger equation by a set of Hamilton-like equations for the evolution of the nuclear positions and momenta. And this we do it by basically replacing the nuclear time-dependent Schrödinger equation with a Hamilton-Jacobi equation and solving these partial differential equations with the method of characteristics. So basically we introduce an infinite set of ordinary differential equations for the evolutions of the positions and the momenta, which are the characteristics of the Hamilton-Jacobi equation. And we do this in the classical limit. So basically in my so classical limit for me here means that we neglect the h bar squared term in the Hamilton-Jacobi equation, that is the so-called quantum potential in a hydrodynamic description of quantum dynamics. And so once again, this is everything I'm going to say about the classical limit in this talk, because I would like to focus a bit more on this electron-nuclear coupling operator here, because we have to do some work to approximate it, to make it actually computable along in a molecular dynamic simulation. And basically there are 2 points to be addressed when it comes to this operator U. So first of all is how to treat the dependence on the nuclear wave function here when this nuclear wave function does not exist anymore, because we have replaced it with trajectories. And Hardy has talked a bit on Tuesday on how to do this. And so also I'm not gonna describe these into details today. However, I'm going to focus on this other point. So are all the terms in the expression of this electron-nuclear coupling operator equally important? And I would like to talk about this because I think it's somehow related to what Caroline Lasser has talked about yesterday, and was also mentioned by Irene Burkhardt in her talk yesterday. And so I think maybe one can find some connections between what we have done to treat this operator here and their work. So the questions came to my mind due to the fact that, in my opinion, this is also what Hardy showed on Tuesday, that the exact factorization is formally equivalent, formally very similar to the Born-Oppenheimer factorization. And also the equation of motion that come out of the exact factorization are very similar to the Born-Oppenheimer equations. And so what I wanted to look at here was like the link, if there was like some kind of limit operation that we could introduce to derive Born-Oppenheimer from the exact factorization, and then exploit somehow this limit operation to understand a bit better how to treat the electron-nuclear coupling operator in the electronic equation. So now just a few words on the Born-Oppenheimer approach. So basically, Born-Oppenheimer tells us how to approximate the molecular wave function as a single product here by assuming the adiabatic approximation. So by assuming the adiabatic separation of time scales of electronic and nuclear motion. So the nuclei being much heavier than the electrons, they move slowly and in some situations, and the electrons being much lighter can adapt instantaneously, almost instantaneously to the new configurations on the nuclei, and therefore always occupying the same eigenstate. And this approximation is summarized in this form here, where the nuclear part of the molecular wave function is a nuclear wave function, and the electronic part looks very similar to what we had in the factorization, and with this parametric dependence on capital R, with this dependence here on little r, on the electronic positions. But as you can see here, in this case, in Born-Oppenheimer, the electronic function does not depend on time. And in fact, the electronic term in Born-Oppenheimer is the solution of the static eigenvalue problem associated to the electronic Hamiltonian, with the eigenvalue here that I call epsilon BO. And instead, the nuclear equation is, once again, a time-dependent Schrödinger equation, here in square brackets, again, a Hamiltonian, and the effect of the electrons is all contained in this scalar potential that comes from the solution of the electronic static equation. Now we can look at the two equations a bit more into details. And so what I'm going to talk about today is basically the work that I've been doing with Florian Aisch a few years ago already. And so how do we go? What happens when we go from the exact factorization equations to the Born-Oppenheimer equations? So basically, the electronic equation loses this term here. So it basically loses the term that tells us how the electronic wave function changes in time. But this is because here in Born-Oppenheimer it does not change in time. And we also lose here the electron-nuclear coupling operator. Okay, it disappears in the Born-Oppenheimer limit. And in going from the nuclear from the nuclear equation of the factorization to the Born-Oppenheimer equation, what we lose is the vector potential. And what happens to the scalar potential? It happens that it becomes static. Okay, it loses its time dependence. So now the idea is how do we go in how rigorous way from this equation to the other equation? So here we use we introduce a set of units that allowed us to extract some key dependence in the electronic and in the nuclear equation of the factorization. And I will show you what I mean with this key dependence in the next slide. So this is, and basically, so this is something that has been done also in a JCP paper from 1999 by Cabral and Ciccotti to apply some similar procedures, like similar to what we did here to the Liouville von Neumann equation. So what we did was to introduce some fundamental units: mass, length, energy, and charge. And basically, the units here are atomic units. What we instead did is that we measure the masses, not by using the electronic mass as a fundamental unit, but by using some typical nuclear mass as fundamental unit. And for instance, sorry? Okay, no, I'm not, so it's, we said, for instance, in the paper that M0 can be chosen to be like the average nuclear mass. Starting from these fundamental units, we can derive also some units of time, action, and velocity. And then we can express also some fundamental constants by using dimensionless quantities and these derived units. And we did this for the speed of light and for Planck's constant. And what is particularly interesting here is that Planck constant becomes like this h bar prime, which is dimensionless, and times the unit of action. And h bar prime is equal to the square root of mu, where mu here is the electron-nuclear mass ratio. And I think this is what has been called by Caroline and Irene yesterday epsilon. So when then we do this, so basically we use this new units, or these units, in the electronic and in the nuclear equation, we managed to extract, as you can see here in this first equation, like different terms in the electronic equations, and this gives us some prefactors where we can identify the dependence on the different powers of the electron-nuclear mass ratio. And then, so if we think, if we accept that the Born-Oppenheimer limit is the limit of infinite nuclear masses, so it's the limit that mu goes to 0. So basically this term here on the right-hand side completely disappears in the Born-Oppenheimer limit, and we are left only with this left-hand side term, which I report here, which is basically static. So, okay, this is again, as in Born-Oppenheimer, the eigenvalue, a static eigenvalue problem associated to the electronic Hamiltonian. What else can we see in this equation, basically in this expansion in powers of the electron-nuclear mass ratio, is that we have two terms, one square root of mu and one term is mu, and the leading term is square root of mu. And basically, as soon as you start including terms beyond the Born-Oppenheimer limit, we have here that the time derivative reappears in the electronic equation. So like some kind of like the dynamics appears back in the electronic equation as soon as you abandon the Born-Oppenheimer limit. And you can also see that the leading term, so there is one leading term in this electron-nuclear coupling operator, which is powers mu powers 1/2, and then there is a second term that instead is power mu. Is power 1 and mu. And what we have done then later on to derive this molecular dynamic scheme to solve the electronic and nuclear equations by then including also the classical limit of the nuclei, is basically to neglect completely this second term here and to focus on using only this part here of the electronic equation for non-Born-Oppenheimer dynamics. So then we have to see what happens also to in the nuclear equation. We have to do this the Born-Oppenheimer limit also in the nuclear equation, and so however here we had to think about what happens to the nuclear wave function. Because basically, so if you suppose that your nuclei are described by a wave packet, it makes sense somehow to also expect that the nuclear wave packet changes as the masses of the nuclei change. So basically, if the mass increases, one would expect that that the nuclear wave packet would become more and more localized. So we cannot neglect the mu dependence of the nuclear wave function. And in order to take into account this nuclear, to account for this mu dependence in the nuclear wave function, we used complex phase representation of the nuclear wave function, where we express the phase in a series of powers of mu. And then if one inserts this expression here into the time-dependent nuclear Schrödinger equation, and we then do the classical limit, we end up with this nuclear equation here. And so if you look at them, now they're basically the Born-Oppenheimer equations. Okay, so the electronic equation is static, and the nuclear equation remains an evolution equation, so it's still a dynamical equation, where the effect of the nuclei is contained in in this static potential. So we basically showed that Born-Oppenheimer can be derived from the factorization by taking really the mu to zero limit, which is the infinite nuclear mass limit. And so then we wanted also to do some numerical analysis to try to understand if it makes sense what we did, and in particular here what we.
Am I the only one who lost the speaker?
Oh, you don't. I'm here.
I'm listening.
Yeah, everything is fine for me.
Yeah.
Can you hear everybody?
I can hear. For me, it's okay.
Cesare, can you hear me?
Okay, now I can hear again. Sorry.
Okay. So just here we wanted to do some numerical tests to understand if somehow this studies in powers of mu make somehow sense from the numerical point of view. And so what we did was to focus on this term here. So it's the term basically that is the beyond Born-Oppenheimer, the leading term that is beyond Born-Oppenheimer.
9 minutes, including questions.
Okay, thanks. So so this term here contains a term like this. So it actually makes sense that this term here is the leading term beyond Born-Oppenheimer that induces some dynamics in the electronic system, because as soon as you abandon the Born-Oppenheimer regime, you have some dynamical feedback from the nuclear wave function into the electronic equation by by having this term here that depends on chi in the electronic equation. And if we use the complex phase representation and the expansion in powers of mu of this term here, we get that the leading term is actually order mu to the power minus 1/2. And so we wanted basically to test this dependence here. And so we did just some studies, some numerical studies on the dynamics on 3 model systems. So here, here, and here. So they're basically models from proton-coupled electron transfer. So you have this is the ground state that is coupled with different strength to the excited state. And we studied 5 different masses: 500, 1000, 2000, 5000, and 10,000. And so here you see these colored Gaussians here are the initial states. And they're all centered at the same position. And the point is that we changed the width of each Gaussian such that we have that all the systems have the same energy. And then also what we did was to change the integration time step, because what we wanted to look is basically at the same kind of dynamics. And as the nuclear mass increases, the dynamics becomes slower. And so with to achieve the same result with the same number of time steps in all cases, we had to increase the integration time step. And so just to confirm that this is in fact that we observe the same dynamics for different values of the nuclear masses. Here for this for the 3 models here, I'm just taking 3 values of the masses, 500, 2000, and 10,000, and I'm looking at the final nuclear distribution. And as you can see here at the final time, we can see basically here for the 3 models the same kind of dynamics. And this is also represented here by the mean nuclear momentum. So okay, we calculated the average nuclear momentum for the 3 models as function of the time steps. And then what we did to test our theory about the mu to the minus 1/2 dependence, so that I recall here, we basically interpreted this quantity here as some kind of nuclear momentum. And then if you see, if we plot the nuclear momentum at different times as a function of mu to the minus 1/2, we found that it's in fact like it's a linear function. So the lines here are linear fit. We found that indeed this term here has a dependence mu to the minus 1/2. where mu is basically the nuclear mass. So then maybe I just wanted to thank, so maybe I can go fast through this slide. So the idea here is just to give some information about how we used this analysis of this U operator, this leading term of the operator for additional work. So what we did, for instance, was to treat perturbatively the effect of this leading term of the electron-nuclear coupling operator, to do studies on electron-nuclear electronic flux densities, vibrational circular dichroism, and high precision infrared spectroscopy. And these are all the people that were involved in this work. And this was done already when I was a postdoc with Hardy Gross in Halle in Germany. And also this part here, then we basically designed some approximations for this for the leading term, only for the leading term of the electron-nuclear coupling operator, to do some excited state dynamics, and we also did some applications to molecules. And then recently I started working a bit more into the applications of these molecular dynamic schemes that basically has been derived here, also to treat spin orbit coupling and intersystem crossings and driven systems in the presence of external fields. And I have to mention that we also did some similar studies on the comparison between the exact factorization and now the time-dependent artery approach with still with Hardy Gross and Basile Cruchot. Was recently was done in 2019. And so I can stop here. And the only thing I want to say is that basically, I mean, the exact factorization is a very nice approach, because basically we, depending on what we want to look at, we can like manipulate the equations in different way and look at different phenomena. And what I basically just talked here was just like some kind of a nice analysis that we can do to connect the exact factorization to the Born-Oppenheimer approach. But this was just, yeah, as I said, an example. And this I'm done, and I would like to thank you for your attention.
Okay, thank you, Federica, for this very interesting talk. We have time for questions. Caroline, please.
So, hello.
Hi.
Thanks for the very nice presentation. Of course, I ask for intersystem crossings in your in your derivation of where you see Born-Oppenheimer as a limit. At some point, I expect there must be a condition on non-crossing eigenvalues. Or do you? I mean, how does your exact factorization potential fall on one eigenvalue if there is no gap? Or
yes, no, but because basically the term that couples the states appears in U, is driven by U. So when this is out, basically you don't have it.
Okay, so I ask differently. If the U were singular, you were not you could not smash it by the square root of mu.
Yes, yes.
And then
no,
it would
exactly,
be a different story, right?
But in fact, I mean, this is, I mean, really, this is the real Born-Oppenheimer limit. So, yeah, because, yeah, let's, if, yeah, wait a second, how do I see it mathematically that this goes away? I mean, it's just not possible, even if physically you would have it, so you don't see it, because it's basically, so this cannot happen because in the mu to zero limit, the nuclei move infinitely slow. So there's no, it's not allowed to have this this kind of degeneracy.
Okay. Yeah, I have to think about it, because I thought this would be inevitably there as soon as you somehow come close to Born-Oppenheimer surfaces. I thought that crossings inevitably would pop up. In
yeah, but because it's yeah, because you basically, so the end, so the quantity that you use so basically, so if you have a very small gap, the typical time scale of your electronic motion is 1 over the gap. Okay, so if you have the typical time scale of your electronic motion is so 1.
So is it correct when I say that the gap brings in an additional time scale?
Yes.
And if I would kind of use my usual pen, probably I would have to do a 2-scale analysis.
I think
the limit really in. I see.
I think this could be also another way to do it. Yeah, basically you maybe reasoning more on the time scales. So I'm playing a little bit more with the playing different with the units and maybe using some other typical time scale of so unit of time rather than the mass. So this could be, I think, another alternative to maybe see how this gap appears. Yeah, this could be another. Yeah.
Thanks a lot.
Yeah, thank you.
Next question from Irene.
Thank you for the nice presentation and interesting comments. So if you do similar analysis starting from the conventional Born-Huang expansion, I mean, is there a fundamental difference? I mean, one would sort of naively expect that the conclusions are similar. Did you try this?
No, I didn't try. Yeah, but yeah, I suspect. But usually, you know, to get Born-Oppenheimer from the Born-Huang, you use the delta E, but basically you can use the delta, the energy gap between electronic states justify the fact that the non-adiabatic coupling go to zero.
Yeah, that's
so it's like another strategy.
Yes,
yeah, probably some yeah. This is the way I do it in my classes, in fact.
Yes,
and yeah.
I mean, probably there would be kind of good reasons to select a subset of states, and maybe then the picture would be very similar.
Wait, I lost you a second. Can you say the last sentence that you said?
Oh, excuse me.
I just lost you for 1 second.
If you start with Born-Huang, it might be appropriate to select a subspace of states, of relevant states, and then in the end, the picture would turn out similar, probably.
Yeah, I suspect so, yeah.
But it's a very interesting analysis, thanks.
Yeah. But because also this was like somehow having ideas of what are the terms, because we were working on approximations in the factorization, and to say, okay, so what are the terms in this U operator that we keep, and what are the terms that we throw away? In fact, the terms that we throw away, there are second derivatives of the electronic wave function with respect to the nuclear dependence. And since these terms no electronic structure code calculates, so we had to justify why we throw them away. And I think this is some kind of formal way of saying, yes, we can throw them away somehow. Yeah.
Thank you.
Thank you.
Okay, just out of curiosity, I have, maybe this is obvious, but question is, if you do these expansions and approximations in the variational principle rather than in the equations of motion, do you have an idea whether you would get exactly the same result? Probably yes, but
so variational principle apply to
so you have the exact factorization as a variational principle, right?
Yeah.
So you did these approximations and expansions in the equations of motion, but I'm wondering if you do the expansions in the variational principle, and then you take variations of the approximated variational principle, would you get the same thing? I would expect so, but did you think of it?
No, what I was actually thinking about is something that maybe we could get better behaving, but I'm not sure if there would be difference. So maybe if you actually derive the nuclear equations for, so suppose like, I don't know, I write the nuclear wave function in an approximate form, and then I apply the variational principle to obtain the evolution of some parameters that I put in the expression of the nuclear wave function. So, but this is something like that comes afterwards. So, I mean, since the nuclear equation is a time-dependent Schrödinger equation, I could express the nuclear wave function in a way that I want, and then find the best combination of parameters to get maybe nicer classical equations in this idea maybe of using Gaussians like Irene was doing with the GMCDDH, something like this. But I didn't think about how to start from the
no, you do. It's not, there is really no difference. Instead of plugging the, so you plug the the equations, you do it in the. There is no.
I think no. I think in fact it should be what I'm saying should be the same. Yeah.
Okay, thank you very much again. And so before we leave, I would like to remind everybody that Professor Gross is going to be chairing our discussion today. So it's going to be a lot of interesting theoretical and mathematical chemistry. With this, I would now close the session and we reconvene at 8. Thank you.
Thank you. Carolina, are you still there? Actually, I wrote in a chat to everybody.
Yeah, I'm still there.
No, because I answered to you, but I'm not in the common chat. But okay.
That doesn't matter.
But I don't remember. It might be that I also thought about it, because I mean, this is a work that's
it's a long time ago.
Yes. But I started thinking about it actually last week when you gave your talk about Wus epsilon.
Yeah.
That's why it came back to my mind, and I said, yeah, maybe I can talk about it.
Yeah, epsilon is your square root of mu, but
yes,
you know what I'm kind of wondering, like for the system bus thing with Irene, where we had this var, another small parameter, the var p. I'm somehow wondering whether your underlying assumptions has another thing that something has to be small, and probably step size, or I don't know. Or
it's just that because basically,
you know what I will do? I will read your paper with Eich across the line and write an email next week.
Okay, yes. While I read your papers on the notes.
If I find a point where you brush something away that needs an extra sum, because I somehow at the moment suspect that you have behind the square root, behind your mu terms, somebody who needn't be small with respect to mu unless you put it. You know, otherwise I cannot imagine that you jump on one Born-Oppenheimer surface in the limit. The others are there. Why should?
But it's somehow like. Since so it's like it's physically prohibited to do that, because when the mass is in the real infinite nuclear mass limit, the nuclei move super slow.
But for example, when you have a conical intersection, you can really prove that in the limit. If you send a Gaussian wave packet onto the crossing, you can prove that in the limit the thing goes through.
Yeah.
And I think that such an effect must be hidden in your analysis somewhere.
There was also something that we were thinking with Basile, something like doing very slow, as most adiabatic as possible motion close to a conical intersection, like on the adiabatic surface, and to see if there is this, in fact, this beyond more Born-Oppenheimer effect or not. This because in the end, I mean, then we talk about two singular things. We talk about the singularity of the conical intersection and the singularity of the infinite nuclear mass, and this really scares me a lot.
Yeah, I think these are not interchangeable limits. And my feeling is that with your mu sending mu to 0, I think you have to fix something of the other guy, and to say a priori some boundedness is there.
No, this can be,
Because as you said, when you have something like shrinking gaps and mass tending to 0, you can do stupid things in the scaling of the gap, and you can go everywhere. If you scale stupidly or smart enough, whatever you want.
But Caroline, is this the kind of thing that like Stefan Teufel and Volker Beetz have analyzed? I mean, I vaguely remember that Volker Beetz...
Yeah, but you know, they always know. I mean, what those boys did was they always assumed a generous gap.
Yeah.
And then they went in the mu expansion to arbitrary order, and then assuming analyticity of the potentials even to, they did exponentially accurate. But they always had a gap.
Yeah, I mean, didn't they also use like this super adiabatic representation? Yeah, right.
Exactly. So in order to get higher order estimates with respect to Federica's mu, they started tilting the eigenfunctions a bit.
Right. Okay.
And that was the way, kind of moving the eigenspaces a bit, they could get more accurate results.
Okay.
Which is exactly the super adiabatic business. But to build that, you always need a gap.
Yeah. I think you could be right. Yes, I think maybe there is.
I will read and check. It's maybe I can find a term where I can say, look, Federica.
You impose this. Yeah. No, you're right. Yeah.
I mean, it doesn't. I mean, it makes it even more interesting, right?
Mm-hmm.
Do you assume somehow analyticity as a function of capital R in that it persists in the limit of mu going to infinity?
Yeah. But
with it, that there was this one thing that we found in the context of the Berry phase. Remember that there we looked how the geometric phase that is associated with the exact vector potential, how this behaves as a function of nuclear mass.
Yeah.
And there was this funny thing that in Born-Oppenheimer you get a Berry phase of pi, while for any finite nuclear mass you get the Berry phase of 0. And
really?
And if you look at this, at the, let's say, the nuclear coordinate dependence of the exact electronic factor, that in the limit of nuclear mass going to infinity, you develop a discontinuity.
Ah, okay. But this is more or less what we are talking about, right?
Exactly. Yes.
Yeah.
I have a paragraph in the paper because I read it yesterday.
Example.
We are assuming, in fact, that the capital R dependence, because we are considering that the nuclear wave function depends somehow on the mass, but not the electronic. And I think that it's there where we put under the carpet,
it comes in from the back
like
door.
Yes. I think it's there. Yes. Yeah.
But it would be maybe interesting to say maybe to relax this analyticity assumption and to redo the thing, just putting a spectral parameter and to see how it enters.
Yes.
So what to have kind of two parameters. Yeah.
I mean, still, I will have a look. I will have a look. I think it's really intriguing.
Yes.
Hey, the point is, you have to put a small parameter to make me interested. Otherwise, I'm lost,
Yes.
I need a small or a big parameter. Cool.
Yeah.
Okay. So discussion comes back at 8, or what was the plan?
No, it's super late, the discussion.
The clocks come back at 8.
Who?
Yeah.
Clocks.
And so you
at 8, okay, yeah.
So Hardy,
Okay.
I've seen your message before. So you so your session is the night session because you're a night guy as always, right? At 11:45.
At midnight.
Yeah, I mean, I wanted to be there for Arthur's talk. So let's say I'm gonna be there from 10:30 until midnight 30. Yes. let's
Hi, everybody.
buy some Prosecco. Hi, Arthur.
See you all. Yeah. So Hardy, is my question more or less clear? I try to make it somewhat specific, but it's quite general.
Yeah. No, this reminds me of a discussion that we it ties into this Born-Wang expansion aspect.
Right.
That you need to make sure that when you use the Born-Oppenheimer states as basis functions, like you do in the Born-Wang expansion, you must make sure that they're single value.
Right.
Otherwise, it's not the proper basis.
Well, I wouldn't be so I wouldn't be so strict in a sense that people know. I believe in math. People know how to deal with the double valued or triple valued or whatever, like a logarithm of the complex value. It's a multi-valued function, so it's just the math becomes more complicated, and we generally like to avoid that by adding some extra factors to make functions single valued.
And you have to know how to walk on the Riemann sheet in a proper way, which is
So I guess for on-the-fly dynamics, that becomes like really difficult because you don't want to deal with the investigation of the Riemann surface or Riemann sheet beforehand, like a priori. In a sense, you want to just use the non-empirical information and go from there. Yeah.
How about wave packets on different Riemann sheets?
Yeah,
yes,
it's on my project list now for a decade.
Yes, but in order to do that, in order to do that, you still need to know, I think, that where the conical intersection is, and
you need the connection coefficient in order to know where to go on the sheet. How to determine that in a computation, I have absolutely no idea.
Right. Okay. More later. But I guess now we are kind of more or less in agreement. I guess the statement that geometric phase is an artifact of Born-Oppenheimer approximation, I think it confuses many people. And we discussed that, right? So my stress here is that it's not only in Born-Oppenheimer approximation, it also comes in Born-Juan expansion, as you pointed out already, right?
The Born-Oppenheimer framework,
Yeah, in that framework, exactly. So it's just a feature of representation in a sense, rather than saying that it's an artifact of Born-Oppenheimer is like, okay, if you do something beyond, like the nature of progression is then it's like, oh, I'm doing not Born-Oppenheimer, then I don't need to worry about geometric phase. That
is not the right conclusion.
Yeah, so that's what people arrive to. And
no, I meant the title of that paper in a different way.
Exactly, so, yeah.
I mean, the traditional Berry phase relies on this adiabaticity concept, right? You have the adiabatic parallel transport, right? So you have infinitely large nuclear masses, but and then you move your molecule in a way such that you go around the conical intersection, but you move it by hand, right? It's but in the real world, the nuclei move the way they move,
right?
So in that sense, the Born-Oppenheimer Berry phase is an artifact. It's nothing that would be measurable, right? Probably.
Probably, and yeah, well, that's another thing that people are usually confused about when you say, okay, I move things around conical intersection. If they start thinking about how do you actually do that? So what does that actually mean? And this is like, in mathematical terms, you need to connect the vectors of the electronic Hilbert space at different nuclear positions continuously, right? So that's how you get the change of the sign. But unless you explain that, this statement that you are moving something is not really clear. What does that mean?
Yeah, that's one aspect. You need to say what you're actually doing, right? To increase the influence.
Yeah.
But whichever way you do it, if you do it properly, it's fine. But it's still not the nuclear motion that the nuclei would actually like to move.
Right.
It's a mathematical construction. This is what I meant by artifact.
I see. Although in some problems we were able to make a Gaussian, say, move around the conical intersection, meet on the other side. So that is doable, but not very likely to happen in the general system. Yeah. Okay. Well,
what we were discussing before, Carolina, I will send you this paper where we see that in the infinite nuclear mass limit, the capital R dependence of the electronic wave function develops a discontinuity.
Yeah, that would be super interesting to me. I have to admit that I was completely ignorant about that. It would be great.
And it very much relates to.
You know, I like these kind of things.
Okay. Yep.
Good. So see you later.
See you later.
See you later.
Bye.
Hardy, I send you my question by email.
Hope to see you in the last session.
Yes.
Bye.
Bye.